Um, my name is Ed Hirst. I work at the Jet Propulsion Laboratory, which is part of NASA. And I want to tell you a little bit about some of the things I've encountered during my time working at JPL. So the talk is titled Imagination in Space. And the background there is actually a image that was taken by the Juno spacecraft of the planet Jupiter. So we'll come back to that in the future in the talk. I wanted to start by telling you a little bit about myself. I currently live in Los Angeles, California. I was born in Guatemala. Left there fairly early, spent a year in Columbus, Ohio, then spent 10 years in Panama, then moved to Guatemala for 8 years, then to Austin, Texas for college, where I got an aerospace engineering degree. And once I graduated, I came to work for the Jet Propulsion Laboratory in California, and I've been here ever since. My family has always been part of aviation in one way, and I took that a step further and expanded into space exploration. So the picture of me up in the kind of middle center there is a picture of me in a U.S. Air Force cargo plane. My dad was part of the U.S. Air Force, and this was one of the tours we did on base. The second picture there is me doing one of the things I enjoy, which is bodyboarding. So that's a picture taken by one of my friends on one of our surf trips. And then the bottom two pictures are me during the orbit insertion or after the orbit insertion when we arrived at Jupiter. I'm congratulating the team that supports Juno of that accomplishment. And then you see a cartoon there at the bottom, which I found very interesting. It was made after this event, kind of emulating the picture above it. And you see kind of a little saying that they caught me on in Spanish. So you can read that. So that's who I am. And I'll tell you a little bit more about my work at JPL. I thought I'd talk about 3 examples of some imaginative solutions I've run across during my time at JPL. One was, how do you stop a speeding piece of a comet? You've heard of stopping a speeding bullet. Well, there's one mission I worked on. We were trying to capture comet dust. It's called stardust. So I'm going to tell you a little bit about that. Another mission I worked on was capturing solar wind particles and turning them to Earth. And we had an interesting challenge there in terms of getting those samples back to Earth without destroying them. And that didn't quite go expected. So I'll tell you a little bit about that. And then in my current mission, which is the Juno spacecraft at Jupiter, Jupiter is well known for how much radiation it captures, and that can damage a spacecraft. And so we've done some things to slow the amount of damage that we get on the spacecraft, and I'll tell you a little bit about that. And then finally, just a little bit about how you could get involved if you're interested in the mission at Jupiter that we're doing right now. So on your screen right now is a movie of a particle that is traveling extremely fast and going through a plate. It's, I believe it's a metal plate. And it's traveling at 7 kilometers per second. And why that is interesting, or why that's important, is that when we were flying past the comet to capture dust, we were going to be traveling at about, our velocity was actually 6 kilometers per second. So it's a little bit slower. And some of the dust that we were capturing was going to be traveling at this speed. But you can see that when something travels at this speed and hits something else, it's pretty destructive. You don't end up with a lot of the particle that, skipping ahead, you don't end up with a lot left over from the impact, which when you're going to try and capture particles from the comet, it's important that the particle be preserved. In addition, the spacecraft needs to survive the encounter. So if we're getting hit by a lot of dust, the spacecraft's not going to survive and the dust is not going to survive. So that was part of the challenge that we had with this particular mission. So there was two parts to this problem. One is protecting the spacecraft. And we came up with these, what we called Whipple shields to protect the spacecraft. In the upper right, you see the spacecraft in a configuration where we're flying past the comet. And these Whipple shields were placed in front of the main part of the spacecraft and in front of the solar arrays. On the upper left, this is the spacecraft when we were building it here on Earth. And the blow up is showing you a better view of what these Whipple shields, where they were located. And then on the lower right, you see the shield that was in front of the main spacecraft bus. And it had a metal part and 3 mylar sheets that would allow the particle to penetrate the first one. And as it progressively went through each of the shields, the particle would disintegrate, thus protecting the spacecraft and protecting the solar arrays. So that was one way we took what you saw in that video and just made several layers so that the particle itself never made it past into the spacecraft and the spacecraft was protected. But that meant the particle that was hitting, the dust that was hitting the spacecraft was being destroyed. And the reason we were there was to capture the dust, not destroy the dust. So how did we solve that problem? Well, there's an interesting material called aerogel, and that aerogel is a good insulator, as you can see by the picture on the left, where there's a blowtorch under some crayons, and the crayons are not being destroyed by the heat because of the aerogel. Right below that, there's a brick, a standard brick that's being held up by the aerogel. And so this material is very strong and very insulating. But the other characteristic that it has is that it's very good at stopping particles that are traveling very, very fast without destroying them. And that's the picture on the right. The picture on the right is actually from the Stardust mission, where if you look at the very end of these carrot-like trails, you see a particle of dust. And we use this material to capture the dust without destroying it. This material is about 99% air. It's made out of silicon glass, but as you can see from the pictures, it has very unique characteristics. The middle picture is actually the capsule that was used on Stardust to capture the dust, and all of this aerogel material was placed into the tennis racket-like thing that's sticking up above outside of this capsule. And you can actually see where some of the dust actually blew out some of the aerogel sockets where it was stuck. And that's how fast we were traveling. But there was enough of this material that stayed inside the tennis racket and captured the dust. So, we took a material that was not necessarily thought, whose primary use wasn't necessarily to capture dust, but we repurposed it, and via experimentation discovered that it was very good at actually slowing dust down and capturing it without destroying it or modifying it too much. So that was one solution that we came up with for this particular Stardust mission. So let me move on to the next one. The Genesis mission. The Genesis mission was all about capturing solar wind particles. And what you see on the screen is the surfaces that were used to capture that material. It actually turns out that these surfaces were very delicate. They're very fragile. And one of the challenges we had was once all the material was captured, all of these collection surfaces that you see would stow back in amongst themselves, and this capsule would close back up, as you see in the picture in the upper right. And once that capsule was closed up and we were near Earth, it would separate from the main part of the spacecraft and enter the atmosphere, which is the two figures on the lower right of the picture. So how did we get it from space down to Earth without shattering these collection surfaces? Even the collection surfaces were so fragile that even just landing on a parachute on the ground would be enough to damage them. So we had to come up with an innovative solution on how to do that. And what we did there was we actually borrowed from other applications. What you see on the screen is a very old picture of a Air Force plane that is capturing a film canister that has been returned from space. This was in the 60s that this was done. You see the film canisters there at the bottom of the parachute, and it's running through the parachute. This airplane has these two bars extending down, and it's running through the parachute with those bars and capturing the parachute from preventing it from landing. So we took this application and applied it to what we wanted to do. But one thing that we learned is that doing the capture this way was very dangerous. It was dangerous for the film canister, and it was dangerous for the pilots. So we made some changes, and that's what this next video shows. And before I run the video, what you see on the screen is a parachute in the form of a parafoil. So it's a parachute that glides, much like more modern parachutes do nowadays. You don't see very many round parachutes anymore. But this parachute glides, and then you see a helicopter that has a pole on it. So let me run the video so you can see what is happening here. The fact that the parachute was gliding gave multiple opportunities for the pilots to come up from behind it and collapse the parafoil. Let me run that again. Collapse the parafoil with the bar, and it had a hook at the end that would capture the parafoil itself and allow it to be captured securely rather than slide back off the pole and the hook. So let me run that one more time in case there's some buffering. And some of the black you see on the screen is it's an old video. So that was a solution where a problem where we we knew a parachute, the normal parachutes wouldn't work, so we had to go and borrow a solution from somebody else and apply it to what we wanted to do. Unfortunately, the little parentheses that was in one of my earlier slides, things didn't quite work the way we were hoping they would. Not because the parachute or this capturing system didn't work, but because of something else. So let me get that video rolling, and hopefully I'll get the sound to come through. So I'll just let you listen here for a little bit. So this video was taken from the landing site as we were trying to track the capsule and direct it towards, direct the helicopters to go do what you saw in the previous video once the parachute was deployed. You can see that there is no parachute that's come out. Let me see if I probably don't have enough volume there. So I'll just let you listen.
We can't hear.
So needless to say, this was not a fun day. I was in the control room when this was happening. I was in Pasadena. This was happening out in Utah where the landing site was. So sometimes things still go wrong. And like I said, this particular instance had nothing to do with the parachute itself, but rather a piece inside the capsule. So what you're looking at on your screen is a switch, an electrical switch, and you see that there's a gap between kind of the two, kind of in the middle off to the left of your screen, there's a gap. And you see these kind of vertical lines that are going up and down. Those vertical lines are a spring. And the way this switch was supposed to work was when the left side of the switch encountered a force, the right side of the switch would, the right mass would move towards the left side and close that gap and close an electrical connection. As it turns out, this switch, when the spacecraft was built, was put in the opposite direction. So, and when we did testing, we didn't realize that that's what had happened. The tests weren't enough fidelity to realize that that's what had happened. And when so the side that got the force on it pushed the mass away from the electrical connection instead of towards the electrical connection. And so the electrical connection was never made. And the capsule never sensed that it had arrived at an atmosphere and didn't trigger the sequence to deploy the parachute. And then you saw what happened in the video. But the good side to this story is that not all was lost. The science community did go out to the site, and they cleaned all the samples, and they gathered them all up, and they cataloged them, and made them available to people to go off and do their science investigations with it. So these kinds of things happen often, not often. They happen on occasion, and you sit down and you kind of examine what happened, and you learn those lessons, and you apply it to the next mission. Let's see. The last story that I have for today is, oh, wait, one more part. For those of you familiar with the Roadrunner and Wile E. Coyote, I figure this cartoon came out shortly after this event happened. And so we got a kick out of it. You always have to find a little bit of humor in things that happen that are not enjoyable. So I thought I'd share this cartoon. It made us a little less frantic on that day when this all happened. So my last story is about my current mission, Juno. And there's a trailer that came out before we arrived at Jupiter, and I'll just play this and let you listen to the trailer.
The scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown. Nothing's really certain about what's going to happen.
It's a monster. It's unforgiving. It's relentless. It's spinning around so fast, its gravity is like a giant slingshot, slinging rocks, dust, electrons, whole comets. Anything that gets close to it becomes its weapon. And it just so happens, deep inside this body are the secrets we're after. Secrets about our early solar system.
Biggest and baddest planet in the solar system, and it's got the biggest and baddest radiation and the biggest and baddest magnetic field.
The background radiation that we're exposed to on Earth is about a third of a rad. What we expect to see at Jupiter is about 20 million rad. No spacecraft has ever flown this close to Jupiter, flown this deep into the radiation belts.
So the real trick is, we're going to go in close, get the data, and get it. And the first time we go in, that's the most dangerous. We call it Jupiter orbit insertion. JOI.
Nothing's really certain about what's going to happen.
So one of the reasons you go to new places is to learn new things. And you design as much margin as you can into the spacecraft that you're going to. What you heard there is that there was a lot of uncertainty of the kind of environment we were going to encounter when we got to Jupiter. One of the characteristics about Jupiter that I alluded to before is that it has a lot of trapped radiation, and that's what this figure that you're looking at now is intended to describe. You see Jupiter kind of off to the center, and then you see these colored zones, and those represent kind of the intense radiation that's trapped at Jupiter. The other kind of oval lines that you see are magnetic field lines that are actually responsible for trapping the particles that cause the radiation. So one of the things we did was we actually tried to avoid the bad zones as much as we can. And you see the path that's being described there is where we flew the spacecraft and where we still continue to fly it whenever we get close to Jupiter. Even today, when we fly past Jupiter every 53 days, we fly right through this zone where we avoid a lot of the radiation and not close enough that Jupiter is actually, that, you know, we're at risk of hitting Jupiter. We fly this really nice keyhole between those two zones. Let me play that one more time, just so you can see that again. The other thing we had to do is we wanted to use electronics that are more commonly used. All of, or most electronics that are used in space missions have some hardening against radiation. The radiation we were encountering, as you saw in the video, was many, many times what a normal mission would encounter. So our solution to that was not necessarily to change the parts, but put all the parts in what we called a radiation vault. So let me stop the video there. There is a box made out of titanium that we designed, and we put all of our electronics boxes inside of this box. That's what these different colored smaller boxes represent. And this innovative solution of, instead of changing each individual piece part, but rather putting them all in a box that was then protecting all of them, knocked down the radiation by a factor of 800 and has allowed us to survive at Jupiter in this very bad radiation environment, and continues to allow us to fly at Jupiter in this very bad radiation environment. So that was the solution we came up for that problem, where we just came up with this box that we could use and put everything inside. So here, just wrapping up the talk, I wanted to share with you that you too can get involved in our Juno program. There's a website there on your screen, and I'll leave this page up in case you want to come back to it and write that down. But all of the images that we take with Juno get put on this website, and anybody can go in and download the images and make creations from them. So let me get some of these videos running. And you see that some people do really interesting work with the videos where they're trying to map and orient the storms and see how they're moving around. Other people do really fanciful things like imagining an astronaut in orbit around Jupiter. And then this last one, let me accelerate it a little bit, is a little play on the size of the Great Red Spot compared to Earth, which the Great Red Spot is known to be very big and is currently about the size of an Earth or 1.5 Earths, depending on how you measure it. So I'll leave this up. And I thank you for your attention. This has been fun, and I'll open it up for any questions.
Wow. Thank you, Ed. Some great questions here in the chat. Let me tell you about some. Why did you choose Jupiter to send Juno to?
I can't hear you.
Ah. Ha. Give me a sec.
What are you going to do?
Okay. Can you see the chat?
I can see the comment box.
Okay.
So write them there right now.
Mhm.
Why did you choose Jupiter?
If there's any questions that come across the comment box, why did you choose Jupiter? Why did we choose Jupiter as a target? Let's see. Jupiter, when you look at the solar system, and you look at 99% of the mass of the solar system is in the sun. About 70% of what's left over is contained in Jupiter. And the rest of the planets make up the rest of the material. So Jupiter was the first to form after the sun formed. And it's very important the way that what the scientists are trying to understand is how Jupiter is made up today, and how it came into being as it is today. So understanding a little bit more about how Jupiter is formed allows us to understand the formation of the solar system and allows us to understand the formation of planets. And that's why studying Jupiter is so important.
Okay, go next.
Which was the best mission that I've worked on? All of them have actually had their interesting parts. I would say, Stardust was it was Genesis, was the first time we were returning samples since the Apollo days. And it was returning samples from the sun. So that was intriguing in and of itself. Stardust had its own unique parts of it, going out to a comet and returning dust from a comet. So I can't say that I have a particular special one. They've all been interesting as I worked through them. How did I start my career and end up working at NASA? Well, it goes back to when I was a young boy, and I was watching Battlestar Galactica and Star Wars and things like that. So space has always had kind of a interesting. I've always been kind of interested in space. There's an interesting story. When I was around 8 years old, I was part of a letter writing. I had a letter writing assignment as part of school. And I wrote to a company that I picked out of the blue that happened to be JPL, because I was more into airplanes back then, and I thought they would send me pictures of rocket engines and airplanes and things like that. And they ended up sending me pictures of Voyager, of the Voyager mission, pictures of Saturn and Jupiter. And it just kind of took off from there. It was interesting, something that I was interested in. When I was in school, in secondary school, I always liked physics. When I went to college, for a few years in Guatemala, and I studied physics and math. And then when I went to college in Texas is when I picked up aerospace engineering. How does JPL come up with rocket designs?
There.
the history of JPL goes all the way back to I think the 1950s or so, if not earlier. And they were at the forefront of rocket research. At the time, not a whole lot was known about rockets. So even though they started down the rocket path, a lot of what we do today is spacecraft design. And that process is a very collaborative process with the science community, where different scientists come together and say, what are the most important science questions that need to be answered? And then there's a back and forth with the engineers to put together missions that will answer those questions. And then those missions are proposed to NASA to decide which ones to fund. So it's not exactly the answer to your question, but it's how current missions are put together and kind of proposed for funding.
Hi, Ed.
Well, thank you. My example is just, I'm just reading the comments that this is what you want to be in the future. It's very possible. It's very reachable. There's a lot of different, to pull off a mission, to pull off the work at JPL requires a whole lot of different people. Even if you didn't want to be an engineer, you can be a scientist. If you didn't want to be a scientist, there's financial people, there's communications people, there's people who do art. There's all kinds of things that are done at JPL, not just engineering. So it's accessible to a lot of different, and it needs a lot of different people to contribute for a mission to be successful.
Hey, Ed, Lucio Santos really wants to know, how big is the largest black hole?
How big is the largest black hole? I don't actually know. I've never been involved in a mission with black holes that study black holes, and I don't have a science background, so I don't know I can't answer that question, unfortunately. How long did it take to get to Jupiter? For us, it took 5 years. For Juno, it took 5 years to get there. Depending on the size of the rocket that you have to launch your spacecraft, that determines how much energy you can put into the trajectory. And we did, the size of our rocket was such that we did kind of an inner loop that was 2 years long in the inner solar system, and then we flew past the Earth and got what's called a gravity boost, and then made it out to Jupiter 3 years later. So that's how long it took us. If we had a bigger rocket, we probably would have been able to get there sooner, but then we would have needed more. We ourselves on the spacecraft probably would have needed a bigger rocket to slow ourselves down to get captured by Jupiter. So it depends on a lot of factors. Does every planet have an atmosphere? No. There's a lot that have tenuous atmospheres or very light atmospheres. Mars is a particularly interesting atmosphere because it has just enough atmosphere that you have to pay attention to it. Like for the recent Mars missions that have gone to Mars and have landed there, it has enough atmosphere that you have to pay attention that it's there, but it's very little atmosphere. But I think it varies from place to place on how much atmosphere they have. Yeah, I started college in Guatemala at Universidad del Valle de Guatemala. I did 2.5 years there, and then I went to University of Texas at Austin.
Awesome.
I'm not sure if that's a question, the one about the sun. We have not reached another star with anything that we've sent. The farthest active mission that we have going is the Voyager spacecraft, and they're very far away. They have reached what's called interstellar space, but they're not yet at a star. I think the closest star is several light years, so it'll be a while.
So Ed, did you get into a rocket?
Have I gotten into a rocket? No. The closest that I have been to a rocket was for the Stardust launch, where I was, I think, 3 or 5 kilometers away when the rocket went up. And the interesting about that is it was an interesting reminder about physics, because you see the rocket about this far, this size, it's a long way away, and you see it go up. And then when it's, several feet off the ground, then the sound hits you. And it was a nice physics reminder. I see that our time is soon coming to a close.
Right. And we're going to answer one more
How
question.
did I get to work at NASA? Well, when I graduated from college, I had the opportunity to interview with the Jet Propulsion Laboratory. So I had, as I was explaining earlier, I had a aerospace degree, and I applied for a position on the Galileo mission, which was a mission that went to Jupiter. I think it arrived in 1995. But what I mentioned earlier is that there's a lot of different types of disciplines that are needed at NASA and that are used at NASA. So there's many, many pathways to get to NASA. You can be an artist, you can be an engineer, you can be a scientist, you can be a manager, you can be a financial person.
So we're going to start the group fee.
Okay. Go to selfie.
Okay, we have 22 people in the session.
So thank you. This has been very fun for me. I hope you enjoyed the talk.
Yep. So everyone, let's take a group fee, including you, Ed.
You're welcome.
Type in here.
Yeah.
Take your selfie. You have 8 people. You can see us.
Okay, we're up to 10. Let's see if we can get it to 20. There's 21 of us here. Okay, I'm gonna end it in about 30 seconds. Finish your pictures. We're up to 12. Okay, there we go. 13. Yes. So thank you everyone for being here. Thank you, Ed, for your time. And everyone should be getting your group fee on your screen. You can save the photo and it will download.